Welcome to Ready to Derive. In this video, we are going to learn how to solve quadratic equations by the method of completing the square. So let's present a scenario. Here we have a person with a ball in their hand, and they're going to release the ball up, throw the ball into the air. So it goes up, slows down, reaches its maximum height, and then speeds up on the way back down to the ground. So a question we could ask is, how long does that ball take to reach the ground? Well, we would need a function for that. So with a little physics and math, we could create this equation where h is the height of the ball in feet and time is in seconds. And these are all, this is -16, happens to be half the acceleration due to gravity, which is -32 feet per second squared. The 20 would be the initial velocity, so we're thinking that's 20 feet per second. And the 6 would be the height from which the ball is released. So this is barring a lot of wind resistance, this is actually an accurate equation to model the height of the ball. So again, if we want to ask when would the ball hit the ground, we really need h to be 0. So that would be solving this equation. And now we have a quadratic equation, and we could use the quadratic formula, but the method of completing the square is what you use to actually prove the quadratic formula. So we're going back to basics here. And just have a visual look at this. If I graph h using Desmos, so h on the y-axis, t on the x-axis, I can get an estimate. It looks like it hits the ground somewhere between 1 and 2 seconds. So we will revisit this problem at the end of the video to see if we can do this by completing the square. So without further ado, let's get started. So we'll begin with a brief review of solving quadratic equations by factoring, because this is by far the most expedient method if the quadratic is indeed factorable, as it is in this first one. So we are looking for two factors. Oh, by the way, since I'm treating only the special case where the coefficient of x squared is 1, later in the video, we'll deal with when that's not 1 and how we accommodate that. But for now, so we need two factors of 6 that add to -7. So that would be -1 and -6. And this is easily solvable. Those are the two solutions to that equation. Now let's change, so we still have the +6 here, but now I want the factors to add to -5. Well, we do have another pair of factors of 6, so that would be 2 and 3, and they add to -5. Easily done. But now if I was to tweak the middle term a little more, put -8, I realize that I've run out of factors of 6 to work with. So there's really no integer or whole number combination that's going to make that. In fact, the answer is probably going to involve irrational numbers. And so for an equation like this, you could use the quadratic formula to solve that. But the quadratic formula is actually derived by the method of completing the square. So it's important that you know how to do it that way in order to fully appreciate the power of the quadratic formula. Now, I know you were super excited to dive right into learning how to complete the square, but we're going to have to take a brief detour to review the concept of the perfect square trinomial. So let's factor this trinomial here and see what's special about it. That would factor as x plus 3. And what's special about it is that the factor is repeated. So x plus 3 is repeated, so we can rewrite it as x plus 3 squared. Hence why we call this trinomial, this is a 3 terms trinomial, is the square of a binomial. So it's called a perfect square trinomial. So let's get into another example, and let's see if this is a perfect square trinomial. So x minus, two numbers that multiply to 25 and add to -10 are -5 and -5. So we can write that as x minus 5 squared. Now, so what has to go in this place to make a perfect square trinomial? That it can't just be any number. It has to be a number that gives you, that when factored, gives you an identical binomial. So the way we can think about this is you can think, well, look, let's work in the other direction. We need two things that multiply
that add to negative 8. We don't know what they multiply it to, but they need to add to negative 8 and they need to be identical. Otherwise, it won't be a perfect square trinomial. So I realize I have to split the difference, write this as x minus 4 times x minus 4, which of course would be x minus 4 squared. And that in turn informs that this, if I was to FOIL out that those binomials, that this would end up being 16. So, what is the trick here? It seems like we had to get negative 4, we took half of negative 8 and then squared it to get 16. Well, let's see if that works again. Let's try this. So how could we find what magic number? I like to call this the magic number. So the number that goes here we'll refer to as the magic number, which was 16 in the case before. Let's see again. So we need two numbers that add to negative 2x that are identical. So it must be x minus 1 squared. And then if I was to FOIL out, right, and then multiply these last terms together, I'd get positive 1. So once again, it appears that if I take half of negative 2, which is negative 1, and square it, I'll get the magic number. Did that work here? Half of negative 8 is negative 4, square it, and I got 16. So let's try one more. X squared plus 5x, this is an interesting one. So let's try that method. Let's try it this direction instead. So let's take half of that, 5 over 2, squared, and it seems that the magic number is 25 over 4. Not the nicest of numbers to work with, but let's try that out. So what would we multiply together to get 25 over 4? Well, actually, we just took 5 over 2 and squared it. So that must mean that this must be 5 halves, and this must be 5 halves. 5 halves times 5 halves is 25 over 4, and 5 halves plus 5 halves is just 5x there. That would give us the 5x. So that indeed is the method by which we create a perfect square trinomial. So if I had a trinomial like this, and remember we're using just 1x squared there right now, it's easier to work with it in this form. It seems that the rule is take half of the middle coefficient, square it, and then add it to the trinomial. So that would become, let's see, just to finish off, we'll use blue. So the magic number I'm going to call is b over 2 squared. And we need this technique in order to be able to learn to complete the square, which we'll do next. So the moment you've all been waiting for. Let's solve by completing the square. Let's take the quadratic from before, the one that couldn't be factored. And once again, we're doing this for just when the coefficient of x squared term is 1, that leading coefficient. So I've got some steps listed here, which would be a good idea to take notes on so that you can use them in some of the practice examples. So the first step is to bring the constant term to the other side. So that would put negative 6 over there. The second is now we're in the situation of the warm-up slide before, where we have to think about what is the magic number that we add to both sides to make a perfect square trinomial on the left side. And if we recall, we take half the middle term, so half of negative a is negative 4, square it, and that gives us positive 16, and I would add 16 to both sides. Now, the next step is to factor the left-hand side and simplify the right-hand side. So we should know that this, sorry, let me be consistent here. We should know that this will factor as x minus 4 squared, but don't worry if you have to first of all factor it out fully like this, just to reassure yourself that you're doing it correctly. So you could have factored it like that, but then it becomes x minus 4 squared equals negative 6 plus 16 is 10. Now now we begin to see some new stuff here. Now the only way to really solve that effectively is to take the square root of both sides. You don't want to FOIL back out, because FOILing back out would get you back to where you started. So we're trying to sort of take advantage of the fact that we have a square on the left-hand side. So taking the square root would undo that, and we would get x minus 4, right? The square root and the square cancel out. And now don't forget, if you take the square root of a number, you mustn't forget the positive or negative version. So you got to put that plus or minus in there. And the last step is to isolate x. So that means adding 4 to both sides. And our answer becomes 4 plus or minus rad 10. So there are two solutions. There's 4 plus the square root of 10 for x, and 4 minus the square root of 10. And you can sort of see the aspects of the quadratic formula being starting to kind of appear in this method. So let's do a practice problem. And so I wanted to give you one where you didn't have 0 on the right, because it's not always that 0 is by itself on the right hand side, but the steps still apply. So we have to bring the constant to the other side. So we add 6 to both sides, and that would give us x squared plus 5x. Now I'm already going to create, equals 5 there. I'm already creating space for the magic number, so might as well to be efficient. So, and maybe I'll even write this on the side. So the so-called magic number, that's not an official mathematical term, by the way. Don't use it beyond the scope of this video. So you take half the middle term, coefficient, so 5 halves, you square it, and that gives 25 over 4, as we saw before. So that means we're going to add 25 over 4 to both sides. And we are going to factor the left-hand side. Now, sometimes people get a little confused as to what to put here. And it's always going to be whatever half the middle term is. So it's the 5 halves that goes here. And you can check by foiling out, again, if you wanted to be sure that you got it right. Let me clear that up a little bit. So this is 5 here. And now we're going to have to add 5 and 25 fourths. And 5 is, let's see, 5 is 20 fourths plus 25 fourths. That's 45 fourths. And now we are going to take the square root of both sides. And that would give us x plus 5 halves on the left. And we mustn't forget the plus or minus. And now we can also break it apart a little, because we have the radical of a quotient, so we can do the radical of the numerator and the denominator separately, which is kind of nice because the square root of 4 is 2. And then that last step is to isolate x, like this. And once again, if I wrote this slightly differently, so negative 5 plus or minus the square root of 45 all over 2, you would begin to see once again the quadratic formula emerging. And sometimes you might have to simplify this. Rad 45 could be simplified to 3 rad 5. So just sort of make sure you know if your teacher has that expectation. So now we are going to deal with the situation when the coefficient of the x squared term, often called the leading coefficient, is not 1. So here's an example. The steps are very similar. There's just one additional step, and I'll introduce that. So first step, I think you can interchange steps 1 and 2, but I kind of like to do this step first. It's a little easier to think about what I'm doing to both sides. So bring the constant term to the other side, the constant being the term without an x. And then the new step, the inserted step, is to divide both sides by the leading coefficient, which is 2. And you will see that the effect of that is to bring us to the situation that we were in before. So we can just kind of do all the steps as they were before. So the next step is to add the magic number to both sides. So let's set that framework up. And to find the magic number, you take half the middle term. Half of negative 6 is negative 3. You square it, and you get 9. The next step is to factor the left-hand side. So you should know that that's x minus 3 squared, but if you're not sure, you could always factor first the old-fashioned way. Realize it's x minus 3, And that also helps you to check that you did indeed get the correct magic number. And 2 plus 9 is 11. Next step, take the square root of both sides. I'll just put that in here. In doing so, don't forget the plus or minus, rad 11. And the last step is to isolate x. And you get this. So notice that we keep getting a nice positive number under the square root sign. The discriminant is positive. It is possible to get a negative discriminant under the square root sign and get imaginary solutions, but in this video we'll just be treating real number solutions only. So now let's revisit the problem from the introduction about the ball being tossed in the air, thrown in the air, and wondering when it would hit the ground. And this was the function that described the height of the ball as a function of time. And remember, so for it to hit the ground, the height of it would have to be 0, which means we end up having to solve this quadratic equation. So let's get started. First step is to bring the constant term to the other side, so -6 over here. The next step is divide through by the leading coefficient on both sides, and that would give us t squared, and that middle term would become, or the t term would become 5 over 4t, and -6 over 16 would be 3/8. And now we look to add the magic number on both sides. And just to break this down, because we're dealing with fractions now, so remember you take half of the middle term coefficient, so -5/4, so half of that is -5/8, and then we square that to find the magic number, which is 25/64. And then we add that magic number to both sides. So the next step is to factor the left-hand side. So we know it's t minus something squared. And that something is always going to be this interim number, the one when you take half of the middle coefficient and before you square it. So that's going to be 5/8 there. You can FOIL out just to check if needs be. 3/8 is 24/64. So add that to 25 and we get 49/64. Next step is to take the square root of both sides. That would give us t minus 5/8 equals plus or minus, don't forget that. And the square root of 49, we can actually do that 7. Square root of 64 is 8. So the final step is to isolate the variable, plus or minus 7/8. And it seems like we can sort of break this up a little further so we can get an answer. So 5/8 plus 7/8 is 12/8, which is 1.5 seconds. And the other answer would be 5/8 minus 7/8, which is going to give us a negative answer, so not very useful in the context of this problem. So it appears that the ball hits the ground 1.5 seconds later. So let's look at the graph from the first slide, and we do indeed see, we look over here, that it looks like that's when the ball hits the ground, 1.5 seconds. Now, one other note before we close is that because both the answers are rational numbers, so 1.5 is a rational number, so is -0.25. There's no radicals left in the expression. That means that the original quadratic probably, well, not just probably, but definitely it was factorable. But nonetheless, this shows that even if you're having trouble factoring a quadratic, completing the square always works.
And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.